All right, well, welcome to our talk. It's on genetic malware, or designing payloads for specific targets. A little bit myself, I'm Travis Morrow. There is an awesome introduction about me already, but so I work at Okta, a little small San Francisco startup, and I do AppSec, mobile, web testing, reverse engineering, pretty much the whole gambit, and I've been doing InfoSec around 11 plus years. And introduce Josh.
So, my name is Josh Pitts, and I wrote BDFProxy, BDF, and there's my URL for my GitHub. And I got into InfoSec back in the 90s by accident. I joined the Marine Corps, got hurt, and they put me behind a desk, and I had to secure Windows 3.1.1 machines. So that's where I got started. So how do we get here? We were drinking coffee. Hold on. There we go. And I'm like, dude, I have this great algorithm that's like a book cipher, OTP kind of thing that you can have some compression. I was like, why don't we do a talk on this and kind of, see what we can do. And Travis was like, yeah, let's do it. So here we are. So if you write malware, you have four enemies, If you conduct operations, you have four enemies besides law enforcement. And here they are. Pretty straightforward, right? Now, when we talk about AV, I'm including consumer-grade products. Now, the problem with AV is it was found by the Charlie Sheen of our industry. That's McAfee, if you know who he is. If you conduct operations or write malware, AV is easy to bypass. It is not really a concern. In fact, I have owned a domain because they were running AV. It's quite easy. Now, I do have respect for F-Secure and Kaspersky. However, we released this back in April to infiltrate the initial version. We had Python and Go executables. There were some Kaspersky people there, and they decided to write signatures. And funniness, just hilarity happened. They ended up flagging the Go loader.
Go itself.
Go itself, the loader, the installer, which is pretty funny. Then they flagged Docker executable. So they were eating all the Docker installs. Then Kaspersky was eating the everything that was compiled with Go. Everything. Everything. Ethereum. Everything. So Kaspersky messed up, right? And that's kind of the point, is that we can actually bypass AV, and it's not that big a deal. So let's move on to the next threat to malware writers. conducting operations. So online sandboxes. I've been uploading malware to programs to fingerprint online sandboxes for a couple years. And there's still a lot of XP out there. There's some Windows 7. And a lot of them have unique environment variables. They don't change their external IP. In fact, you can identify AV companies, you can identify people, coming over tour. You can identify individual researchers. It's pretty cool. And a lot of them have analysis timeouts. So if we can beat that, online sandboxes really aren't that big a deal. Next, the reverse engineer. This is the apex predator for malware. Now, if any of these stupid tricks that you can use against AV and sandboxes, they're not going to beat a reverse engineer. However, if you turn the reverse engineer into a password cracker and take out the analysis part, then you beat the reverse engineer. And all you need is really enough time to finish your operations for just enough time just to finish what you're doing, whatever it is. So if you turn a reverse engineer into a password cracker, you win. Now, the reverse engineer leads into what I call online gaming of like whack-a-mole. Crowdsourcing, crowd sharing. Basically, if you can stop the reverse engineer from providing output to crowdsourcing, you're going to win, right? This happened years ago with Kaspersky, and we're going to go into this, but this is just, it's just crowdsourcing to me is kind of like open source software, right? You think that 1,000 eyes are going to help you, but really, not many people are contributing to crowdsourcing. I didn't see that. So how are we going to do this? Well, we're going to use environmental keying. And this is not a new concept. we're going to go over the last 18 years of environmental keying, and we're going to do it quickly. So the first paper I could find was in 1998, the same year that I got hurt and got into InfoSec. It was by Schneider. And this is probably the best paper and most clear paper on actually using environmental keying. It's obviously old. I mean, you have mail messages, you know, like it had different like Usenet. Yeah, Usenet. That's a good way to do environmental keying. So it was a very good paper, but of course, you know, being that it was academic, there was no POC. Then there was a paper by Core Labs back in 2003, and if the person that wrote this is here, I would love to talk to you. They did not reference clueless agents from what I could see. They talked about defeating reverse engineering and analysis, and they make mention of using an OTP, and there's a lot of math. I was in the Marines. Too much math, right? I was like, I don't understand this. So again, there was no POC. Maybe they made a product. I don't know, but there was nothing public. So then the Bradley virus. Great paper by Eric F. References clueless agents. Talks about using nested components that decrypt whenever they see new things, and it keeps going, keeps chaining. And there were things in the paper, they're like, oh, well, we don't have complete source code. It's not available. Because there's a great concern with the antivirus community if we release this. So of course, there's no POC. Next, hash and decrypt. This is a good concept. It refers to gaming. Like let's say you're playing an RPG, and the game doesn't unlock certain concepts until your character has the right keys. Like the game literally does not decrypt the next part of the game. And of course, this is all conceptual, and there's no POC. You can see a trend. And then there was Uber malware, again by Eric F. And Renal. So they were talking about plausible deniability. So they had a one-time pad, a small script that would, based on environmental factors, would come out to something else. And that's pretty cool. Again, no POC. And then impeding automation. This came out in 2012, and they didn't read any prior research. They didn't even see the clueless agents paper, the Bradley virus. They rediscovered everything. It was amazing, absolutely amazing. They went through, and then they had great quotes. Due to time constraints, we're not releasing anything. Exceeds the scope of the paper. At the inception of this paper, concerns were raised. So they did, of course, they had no POC. So you're telling me, in 18 years, there's no public POC. But we do have malware. Yeah. So we had the flashback malware in 2011 that was Mac only, that would take the UUID off the server, off the client, send it to the server, MD5 hash it, and then send that back down to the client so that it would decrypt on the client. This was an active, this was a public active botnet or infection scheme that actually was very successful. It took months to take it down. And if they used more factors than the UUID, I think it would have taken longer. And then we have Gauss in 2012. Who here has heard of Gauss? Anyone? A couple people, all right. So this is the malware that Kaspersky asked the crowd for help with. It had an encrypted payload. It would take and look for a path. It would MD5 hash it 10,000 times and then see if that was the key and then decrypt in memory. To this date, at least till today, it has not publicly been disclosed that it's been decrypted, but we decrypted it. Yeah. We ended up finding out that it was a LinkedIn invite from Edward Snowden. I tell you, it's good marketing. So also there's a factor to malware, this type of malware. You know, like, how would you use this to compare it to biological and chemical agents? Well, chemical agents, the way they work is like area effect weapons, right? They're effective for days or weeks. And the way you can do this in malware is you set domain-specific environmental factors, right? Like external IP address, you check system time, that kind of stuff you can do on the client side. And these are going to be used for keys to decrypt the payload, right? And also there's biological agents. There's, you know, viral. There's on Wikipedia, if you very authoritative source, if you look at ethnic weapons, they actually target your DNA to see these weapons target who you are rather than just infect everything. So how would you do this with malware? Well, you would look at the path like Gauss, and then you could use like a book cipher or one-time pad to actually make sure that the file is on the computer that you actually want to use, right? There's different ways you can do it. You could use a SHA of the file. You could use a location of the file. You can use what we have as an offset table, right? And then Jacob Torrey at Hack in the Box 2016 talked about puffs, and those are physically unclonable functions. Those are pretty cool, and I suggest you read his paper because this guy's really smart. And this is some really cool stuff. So go ahead and look at that also. You can use that too. So how would you use this malware in your operations? Now, the idea with this malware is you can infect everything, but it's only going to work on certain hosts. It's not going to work everywhere, right? And that's kind of the point. And you can have operational plausible deniability. So you can actually give these agents to people that will deploy them, but can't reverse engineer them. So if you have a large organization, you can give them out and just say deploy them on these hosts, and they can do it, but they can't figure out what they're for. And then you can have hidden command and control. So you can have, for example, let's say you're targeting 4 computers in the world. You don't know where they are exactly. So you start going on a rampage. You start infecting everything you can. And then finally you get this one computer. But by this time, your deployment command and control has been taken down because malware must die got hold of it. And they're like, oh, God, this is horrible. And you take it down. Next, you set up another one. You're like, whatever. You rewrap your malware, change some of the factors. You deploy everywhere, and you find another machine. And this continues, right? This continues on until you have all your machines that you want, and you're done. And no one knows your hidden command and control because unless they were able to see it happen on the host you were targeting. Now, could you imagine a world where this was happening everywhere? Would it be a cyber Armageddon? No, I don't think so. I think a lot of vendors will cry foul. I think that there would be a lot of disappointed people. But then they'll come to realize that, man, we could sell something. We could totally fix this problem. You know, this is like the next APT, right, if this was happening everywhere. But, so we're going to talk about what we did. I'm going to pass it over to Travis.
Thank you, Josh. So our idea was we would create a tool that does just this. And we called it Ebola, which stands for Ethnic Bioweapons Limited Access. It's ethnic because it's based on specific group attributes of the company. It's bio because it changes based on the environment. And it is limited access due to the ineffectiveness of reverse engineers on a global scale or even a macro scale to reverse engineer your specific payload. So just like the Greeks at Troy, as an attacker, we are interested in getting in, but not just getting in. We need to get in stealthily, stay there, and have some sort of protection until we're ready, until we find the right host. So that's what our tool does, is it helps you to protect your payload so that you get in and it is executed at the right time on the right system at the right location. And most importantly, you don't get your specific payload reverse engineered. That's the big thing, right? Like keep your 0 days or keep your targeted malware specific. So we take quite a few different input types for your payload. We support 32 and 64-bit DLL, executables, PowerShell, as well as Python and straight shell code. And we have 2 main protection types. We have symmetric protection using either environmental variables or a specific file that's unique to your target. And we offer OTP, which is a kind of book-based similar cipher that is based off of a unique file in the environment. And our 3 output types, these are what gets loaded. These are what you would send to your client or your target. And these would be a Python loader, a Go loader, or a PowerShell loader. It's your choice. So a little bit about the framework. We tried to make it very modular so that it could be easily extended. So the 2 really important files is the ebola.py, which is kind of the brains. It reads in the genetic.config, and it will go through, parse it, and based on what you configure, it will go through the rest of the file structure and pull in just the components you're asking for. Josh is going to go over the genetic.config configurations right before we do demos. So if we jump into the encryption folder, we have our 3 types. We have environmental keying, we have full OTP, and then we have key-based as well. And if you go into the templates folder, you see that we have Go and Python. We've recently added PowerShell as well. So if we jump into the Go one, we'll see that some of the similar stuff we've been discussing. We have environmental, external IPs, system paths. So whatever you're using gets added, but anything you're not using is not added. So that's really important for signatures, and if they're looking for detection, they're going to have to be looking for multiple combinations of your loader as well. And the payloads, this is how we launch your executable. So right now, we have memory module and Go, as well as straight assembly for shellcode. But if you were to write your own unique memory ability to launch executables, then you could add it in here and call it. So we're going to talk about some of the symmetric protections. This one, specifically environmental variables. So this can be a wide range of things in any combination you would choose. So you can have a limited number of actual environment variables on the system. It doesn't have to be the normal ones like temp, username. If there's something specific to your target, this can be one of the things that is used for the key, as well as a specific path. So if you know that they all have something in common, then you can further target this, as well as an external IP range. This is going to be a 8, 16, 24, or 32 option here, and as well as a time trigger, month, day, or year. And so in order to build this, we're going to create a payload hash. So this is a hash of your malware, your 0-day, but if you notice, we're doing offset bytes. So this is really important so that someone can't just look at a list of known like virus total, right, hashes, and say, oh, I know you're dropping this. So this is going to be configurable by you during configuration, so that if someone is looking through your loader, they can't determine exactly if they've seen this hash before, because hopefully you're changing this every time you launch this on different clients. Also, so then we generate the key. So we take all the tokens, the different pieces of environmental information, we put them all together, and then we use iterations. So we do a SHA 512 hash times 10,000 is our default, but you can do it as much as you want. But if you did it, say, like 1 million, you're going to be spending quite a long time on every single host that you run this on. And then we create an encrypted blob. So we use that key to AES-CFB for everything except for PowerShell. And PowerShell is CBC due to some incompatibilities and no CFB on PowerShell. And so now for decryption. This is what happens when you launch the loader on your target environment. So we actually retrieve all the environment variables for that system, and then we're going to traverse the file system from your starting point. So if you set it high, it's going to take a very long time. If you set it closer to where you're looking for, it's going to take much less time. But remember, if your goal is to prevent the defender from being able to have an idea of what you're looking for, setting it higher up to say like program files or Windows or something like that is a better idea than saying C program files, my accounting software, right? So, and then we're going to combine every single file we encounter. So we do this process for everything, regardless of whether we think it'll work or not. We actually traverse the file system, combine all the environment variables with that current file. We create the key, do the iterations, and decrypt. And at that point, we check what comes out versus what the hash was of your payload. And if it matches, then we execute. If it doesn't, we continue on through the file system. All right, so similar vein, this is still symmetric encryption, and this is, we're going to talk about how we're using a unique file. So the idea here is that as the attacker, you're going to know something about your target. If you know they are running this version of, say, like a database software or an accounting software or anything you're looking for, then you would be able to download that and take some unique executable from there and use that as your pad. And so the idea is that either you've been on the host before and you're just trying to propagate without them reverse engineering some specific targeted malware, or you know about them, and like I said, you've downloaded the software, and you take that file, and what we'll do is we'll create the payload hash like we did previously, and we'll read a location, a random location in the file. Then we're going to SHA-512 it times iterations so that, again, this is time complexity here, and we're going to make that the key. We're going to encrypt your payload with that key. And on the decryption side, this is what happens once it's loaded. Similar process, we start from wherever you tell us to in the file system. We go through and read every single file. We jump to that location, we read out those bytes, we do the hashing, and then we check, do the payloads match? If the payloads match, then we go ahead and we execute what's been decrypted and win. So we've discussed our symmetric encryption options. Now I'm going to go over and talk about our OTP or book cipher options. So I kind of like to think of it as Transformers. As a kid, I grew up watching Transformers. So you take a perfectly, innocuous car and you turn it into an Autobot. So it's similar to that. We take a known good file on your client system, and we build a lookup table that will allow you to take that good file plus the lookup table and create our payload. So it's a pretty straightforward concept. As you can see, we have locations in the file and how many bytes to read. The way we create our pad is similar. We create the hash of your payload, and then we create one unique thing here is we create a 10% hash. So part of the issue we ran into with this is on very large files, it takes a very long time to create these lookup tables. So we did a 10% match so that we could get a good balance of time trade-off to complexity for the defender and as well as attacker. And what we'll do is we'll create the payload hash and then the short payload hash doing the SHA-512 with the iterations of your hash, or your payload. And then we're going to create the lookup table. So the way the lookup table works is similar to how we're showing here is you see that there's 3 bytes we're looking for in the attacker payload. We search in the target binary and we find them, and then we enter them into the lookup table. So it can be 3 bytes, 6 bytes. We generally, in the configuration file, we search up to 9 bytes, because the more bytes you get, it's almost like compression, right? But if you had a whole bunch of 2 bytes or 1 bytes, then you're going to have a gigantic file. Decryption, similar process. We're going to traverse the file system again. We're going to open each and every file. We're going to build 10% of this lookup table. And then we're going to check and see if the output matches the 10%. So far, we've never had it where if it matches the 10%, it doesn't match the 100%. But we'll go back through, and then we'll build the rest of it out and execute your shellcode. So one of the things we were discussing in interpreted languages like PowerShell and Python is your loader protection, because once you drop the script on the host, often they can get an idea of what you're doing as to how you're loading it. Are you doing it in memory? Are you dropping a file? Are you modifying something else and replacing? That sort of stuff. So we actually protect the loader too. So this is the part that actually, once we have your payload decrypted, then we execute it. So we've encrypted that as well. So once the payload is decrypted, we then go and decrypt the loader as well with the same protection that you've chosen for the payload. And our outputs, aka cyber pathogens, according to the FBI, is Go, PowerShell, and Python, as we discussed earlier, and these are what runs on the target systems. And PowerShell is new. So a quick rundown of kind of what we support is for Python, we do 32 and 64-bit executables on disk, and shellcodes in memory, as well as Python code directly supported, and file drop. We had a lot of issues with the DLL injection.
Yeah, we had reflective DLL on 32-bit working. It was really kludgy. Then we tried to work it the same way on 64-bit and just die in a fire.
Yeah.
So we just took it all out.
We took it out.
But
if anyone has some awesome, like rock solid Python DLL injection
reflective
stuff,
injection, then yeah, it was really kludgy. I could talk to someone about it. It was dumb, but it worked.
Right. And so we have Go. Everything's in memory on Go. We have the reflective DLL injection, regular DLL injection, executables, shellcode. Pretty much everything in Go is in memory. And new is the PowerShell. So we just added that, and again, that is also all in memory. So we don't drop your payload to disk, which is a huge thing because you never want forensic evidence left behind of your actual payload.
And a shout out to basically our PowerShell payloads, the actual loaders were brought to you by these folks. I mean, they did great work, and it was easy to take their scripts and pretty much modify them very little, if at all, and use them as loaders. Yeah. So we just had to write the actual encryption, the actual file parsing and all the other stuff to make sure it was compatible with our Python build scripts. Right. So
we definitely appreciate the community for helping with this stuff. And we'll pass it over to Josh for the usage.
All right, so this is how you execute the Ebola script, and that's it. All right, we're done. No, just kidding. So the config, all the details are in the devil's in the details, I guess, right? So the config file, there are 3 sections. There's the overall section where you get to pick which encryption you're using, the OTP settings, and the symmetric settings. So for the overall section, you basically make the option, I'm going to use bookcipher/OTP or environmental, right? And then you have, I want a Go, Python, or PowerShell output. And then you have all the options there for Go, Python, and PowerShell that are available. And you set one of those. And then your key iterations. Again, if you, right now it's at 10,000. If you set it to 1 million on this MacBook Pro within, it's not even a year old, it's about a year old. 1 million iterations on SHA-256 12 takes a second. So if you really want to slow down a password cracker or GPU, there you go. Now the symmetric key settings, this is if you picked environmental. You can set your environment variables that you're using, the path and IP ranges, and also system time. Specifically, you can, for Python, you can actually run this on OS X. We don't advertise it, it's kind of like you use at your own risk, because you can put whatever environment variables you want. If you set environment variable equals empty parentheses, that means it's not being used. So you can create whatever you want. It takes it on the fly and makes it part of the token or the key that gets used for decryption and encryption. Also a path. So this is a static path. Again, you could use POSIX. I mean, you could use Linux, Mac, and Windows, but really we're just focusing on Windows right now. And then also the start location. So let's say you're looking for something in app data, right, or local temp. So you can just set, the actual location, and it supports shortcuts on Windows. And then for the symmetric key settings, you have specifically like an external IP mask, right? So you can set it, to any, /24, whatever, 0. You can do that. And so if you want to target a specific organization that have a very large IP range, you can do that. And then also time range. I mean, this is basically just for the POC. You can set it to a year, a month, or even specifically to a day. So that's kind of neat. Now it's time for our demos. And just to let you know, at Immunity, this is exactly what happened. It was crash and burn. Like, the video's up, and they just posted it a couple days ago, and it's pretty embarrassing. It's pretty bad. So we have videos. So what we're doing is, let's say you have an American in Paris, in Russia, that's low on rubles, and he wants to play StarCraft really bad. So he's gonna BitTorrent a cracked game, because that's what you do, right? And unfortunately, all the cracked StarCraft games have been patched with the Backdor Factory. And we're going to download and execute our environmental key malware that actually goes after a certain version of BitTorrent. So the way it's going to work is we're targeting BitTorrent, this specific version. We're using our book cipher. We're going to have an interpreter, reverse HTTPS that's going to be deployed through a Go executable in memory. And then, so we'll go ahead and this is how it's going to work. You have your torrent, downloads the game, and then the executable is downloaded by our loader, by the game itself, the cracked game. and then memory execution, and interpreter HTTPS gets loaded in memory and connects back to the CNC. So let me go ahead and, oh, this is going to be tough.
It's the first
I know. They are in order. So what you can see here is we have our build script. It's all automated. We did this for the demo because you have to compile your Go executable. And then we're setting up the server, and we're going to be launching Metasploit. And the user executes the game, it dies, and then you have a session. It's pretty straightforward. And it can be quick, depending on what you're using. Go is much faster than Python and PowerShell, that's for sure. So it looks like it's continuing. Let me, I can't get out. No, I can't see anything. Could you?
Just kill it.
Hold on. I don't want to kill it.
No.
Sorry. Yeah. All right, we're just going to bring this in. All right. All right. So we're just going to go into the next demo. So the next demo is the same. No. All right, so the next demo, we're going to, same idea, crack game, Ebola Go payload, and then we're going to be deploying a puppy exe in memory, and then it establishes the puppy CNC. So yeah. Again, this is the build script. All right, we launch Metasploit, or we launch Puppy, or Puppy, however the developer pronounces it. And then we get a session. Pretty straightforward. So this next demo, demo 3. So this is a layered, this is basically a layered demo. We're working backwards, so our final stage is going to be a Go executable launching a puppy DLL in memory, and then we're going to use a Python, using PyInstaller, compiled PyInstaller, is going to look for some environmental factors, and it's going to dump the Go executable, and then Go is going to dump or inject the Python, or the puppy DLL in memory. So it's chaining, and it's delivered through the same method. So this is a little bit longer. So this is working backwards. So right now it's building the Go executable. They already built the Python one. Or sorry. No, actually, this is building the Python one. It's working backwards. So the user executes StarCraft. And there you go, we have our session. So it was chained, it started with Python, went to Go, then executed a DLL in memory. And next, we have our next demo is PowerShell. So we're going to do that. So what I'm doing here is I'm taking from PowerShell Empire. I'm taking the base64 encoded launcher, I'm putting that into a just a file that we're going to deploy. It needs to be ASCII encoded.
Not UTF-8.
Yep, not UTF-8. Then we're going to execute Ebola. And you can see here that I'm actually, the key, the entire key is the desktop name, and then desktop name, IP address mask, today's month, and then a full path, okay? So I'm going to copy that over to the victim machine. I'm going to execute it. And this is debug output, right? You don't want to have this when you deploy.
Yeah.
Now, you'll notice it failed. The reason it failed is because I was looking for a file named demo.ps1. So I'm just going to change the name to demo.ps1, because that was part of the key, right? So that didn't exist on the desktop, so it failed, right? That's what you want. So I rename it just to show that it works. Then you see code execution function, right? It hit it, it matched. And if you look, I get the agent connect back. So there's our demos. Thank you very much.
Yeah.
So we have some known issues, bugs. Oh yeah. So we have some known bugs. So if you if you try to launch Go from inside Go memory module, it's horrible.
Right.
Don't do it. PyInstaller, launching PyInstaller, you lose namespace. It's pretty hilarious. It's like, I don't remember anything. If you try to go with memory module, right, because you're supposed to launch in memory with PyInstaller, no, because PyInstaller writes to disk, and so it can't find any of its supporting files. And also the Metasploit x86PE executable, the DLL is fine, but the PE executable does not work with memory module because they overwrite the reserve section of the PE header, and memory module thinks that it's actually like part of the load config, and so it tries to load that stuff and everything dies. Also, with our one-time pad book cipher, there is potential, depending on what you're deploying, if you're deploying an executable, there might be a way to figure out, this is where the MZ header is, and so like within the pad itself. So there might be a way to help a defender out there. There's also other ways to attack this, and I think if anyone comes up with ways to attack this and want to publish on it, go ahead. I mean, this is all for fun, yeah.
Right.
So if you do this, Go installer, Go with an executable, this is fine. PyInstaller with an executable, and then chaining PyInstaller exe to Go exe. And then technically, you could actually chain PyInstaller or PowerShell with the Go exe also,
Right.
because what we're doing we're using the reflective PE injection, and it works great with most executables. So our roadmap, we're going to continue to build this out, some C++ loaders. We're really hesitant to release those because it can get fingerprinted in a heartbeat, right? But there's additional execution stuff we want to do, better chaining of payloads, and we're looking at doing OS X Linux support for in-memory stuff. So we want to keep everything in memory as much as possible. Any questions? We've got a question on the front row.
Hi. Hi. Oh, okay. So, what would you do? I mean, you're constantly like, what's the word? Like, traversing the whole thing, and doesn't that like, if you're constantly doing that in a loop, couldn't you just like overload the system, and wouldn't that be something undesirable? I mean, because it could attract attention to the thing that you're actually infected and stuff.
Yeah, so the question was, I guess everybody heard him, he has a mic. So yeah, that could be something that defenders could look for. But a lot of software traverses the file system. AV does all the time. So, you know, it just depends if you're looking for it. Yeah.
We thought about putting weights in, but it already takes long enough if you have the whole directory anyway. If you added multi-second weights to like lower the CPU hit, then you're going to be looking at like hours for it to deploy.
And the thing is like you can get closer. If you can get closer without giving away what you're looking for, right? If you want to start like program files instead of C, like start instead of slash, you know, your root, then that definitely speed things up. So the I mean, I think Gauss started at program files, the actual malware. Any other questions? Yes.
Yes. So, what prevents to an AV company to create like a signature on your encryption and decryption mechanism that seems to be fairly unique?
Yeah, definitely the book cipher lookup table would be fairly unique. The AES stuff is we tried to go with APIs or libraries that were native to the operating language, to the language itself. So it wouldn't be out of the ordinary to actually call those APIs. So, and with Go, it's fairly new, and because it's statically linked, and the binaries are ginormous. They're like 3 or 4 megs, like just the smaller ones. It's going to be hard to write a static signature, and I don't think there's anyone that does Go emulation really well yet, as far as AVs.
And Kaspersky tried.
They tried.
And
they
failed.
failed. I mean, they
it's
flagged
not-
every Go executable. Maybe they fixed it. I haven't been keeping up with it, but they definitely took away the signature. I don't know if they actually flagged Ebola properly yet. I haven't checked. Any other questions? All right. Well, thanks for your time. Thanks for having us at
Thank you.
Ekoparty. Yeah.